In this video, you're going to learn how you can build a completely private AI assistant that helps you to work with your files. You're going to learn how you can set up an AI agent that uses MCP tools in order to understand and chat with your files. Hey everyone, my name is Venelin, and in this video you're going to learn how you can build a completely local AI agent that works with tools provided by our own custom MCP server. Our tooling is going to be allowing you to work with your files, read from them, list them, create a small rack from them, and allow you to chat with your documents. We're going to be using LangGraph for our agent, and we're going to be wrapping everything together into a Streamlit UI application. Let's get started. If you want to get access to the complete source code for the application along with the source code for 8 other projects, go and subscribe to ML Pro. There you can find an included complete bootcamp for ML and AI engineers, from foundations to learning how you can build your own machine learning pipeline and deploy it. Then you're going to go through what a RAG, a CAG, tools or tool calling is for LLMs, and what and how you can fine-tune your models and build a complete agentic systems. So if you want to become a better AI engineer, go and subscribe to ML Pro. Thank you. Our project is going to be a Streamlit application that allows the user to upload their own documents and use a AI agent that works with MCP tools in order to help the user chat with their files. So this is the project opened up in my cursor instance, and here you can see the dependencies. First one is going to be the Docling library. We're going to be using this to process PDFs files into Markdowns. Then I'm going to be using fast embed for our simple RAG implementation. On top of that, I have LangChain and some of the extensions of it. For example, the experimental package, the grok package, which is going to be an additional way to use your AI models. Of course, you can integrate this with Gemini, OpenAI, or other models. And the more important part here, of course, is the Ollama instance, since this is going to be the provider that I'm going to be using for my local model. Also, I'm going to be using the LangChain MCP adapters. I had a video on complete tutorial of what MCP is and how it works. There we didn't use the MCP adapters since I wanted to show you how you can actually build the tool calling within your MCP client. But in this case, we're going to be going through an abstraction on top of that, which is going to be allowing us to bind the tools from MCP to our LangChain instances. And I'm going to be using the latest, at least of this recording time, MCP. And now the model or the protocol is mostly using streamable HTTP, which is going to be the protocol or the version of transportation that we're going to be using for our MCP server. Then I'm going to be using Pedantic for some of the classes and return types. Here I'm going to be using PyPDFum for the actual PDF reader itself, Rich for some output in, let's say, prettier logging, and the Streamlit application layer or library that we're going to be using as well. Here I'm also going to be using Watchdog, which is going to be helping us work with the Streamlit. The structure of our project contains pretty much a single directory, which is going to be where most of the source code is going to be put. This is the CogVault directory. Also, I have this data directory, which will contain our personal files, which we're going to be using for the chat with the AI assistant. And here you can see that we have a server and then a client. This is going to be the Streamlit application itself, while the server is going to be the MCP server. Here within the source directory, I have an agent, a configuration file, which I'm going to be actually showing you right now. Here we have the configuration for the Ollama and the grok library. The models that I'm going to be using are primarily going to be the Qwen3 models, both in the variant of 8 billion parameter model and the smaller 1.7 billion parameter models. I'm going to be showing you why we're going to be using both of these. Also here, you can essentially increase or decrease the Ollama context window. This is currently the default value, I believe. And if you have longer files, of course, you can increase this, since the Qwen3 models are supporting up to 128k of tokens. Next, you see here that we have the path for the data directory. The way that we are going to be initializing our LLM models is going to be, again, pretty straightforward. I'm going to be initializing chat Ollama or chat Grok based on the provided model configuration. In this case, I'm going to be passing here also the Ollama context window, along with the verbosity tag, the temperature, and the name of the model itself. Now that we have the setup for our project, we're going to continue with the MCP server. Again, this is within the root directory of the project, and here I have actually opened up the file itself. So in a high-level overview of this file, you see that the most important parts here are the tools that we're going to be providing to our agent, and a summary of the tools is that we have a list files, which essentially is going to take a look at the data directory and give us a summary for each file. For example, the path, the modified time, created time, line count, word count, size, and extension. Then I will have another tool which is going to be essentially reading the complete contents of the file. Of course, this tool will give you a hard time if your files are large. The next one will give you a summary of your file. And here you'll see that we're going to be using a summary model, which is going to be initialized here. In our case, this is going to be the Qwen3 small model or 1.7 billion parameter model. So I'm going to be using a relatively simple prompt, which asks the model to provide a concise summary of the file in 3 sentences or less. So here important thing is that I don't want the model to have a thinking process on top of the response. So I'm adding this no think to the prompt itself. This will still give you the tags for opening of think and closing of think. So I'm going to be removing those, and I'm going to be returning the summary as a string to our AI agent. The next one is going to be the relatively simple RAC implementation that we have. I'm going to be calling this just a search, and this is going to be returning a list of chunks for the documents. For each chunk, I'm going to show you now the structure of it. It's going to contain a document path, the text, and which is going to be the chunk of text, and then how relevant this chunk is to the search query that the model is going to provide for us, or the AI agent. Interesting thing is the semantic chunker. This will roughly have a look at the different sentences for the text, and based on some internal metrics is going to decide whether or not this sentence is going to be actually the split point between this chunk and the next one. So this gives a relatively good chunks as long as you're working with nicely formatted text and markdown files. One thing that I would advise is to use an LLM chunker, which is going to be much better at creating the chunks along with some contextual enhancement or contextual retrieval for the chunks. But in this project, I haven't done this, since this is going to be making the retrieval itself quite slow. If we have a list of file paths that we want to search in, this again is going to be a parameter that our AI agent is going to be providing. We are going to be using that. Otherwise, I'm going to be essentially having a look at all of the files that we have within the data directory. and use those in order to work with them. And the next thing is to actually go through each file, create or get the content of the file, and according to the semantic chunker, split the contents of the file into chunks. And while we're going to go over each chunk, if this chunk has some content, I'm going to be creating or getting the relative path to the document and adding the text along with the document path along with the chunk text right here. So next, I'm going to be embedding the query itself. Note that we are not using any vector database. If you want to do some speed up on your documents, you can also, for example, use here something like Muvush White or SQL White or other local embeddable database for such a simple project that is. And then we will create the chunk embeddings themselves using the embed documents. Note that this embedder is actually a fast embed embeddings that is going to be using the BG small embedder. Recently, I've seen that the Quen team has released a 0.6 billion parameter or 600 million parameter embedder and re-ranker actually on their website and in Hugging Face. Unfortunately, Fast Embed still doesn't support this. I have opened an issue on that, and if they start to support it, I would be very eager to try out this embedder. I'm going to be also passing in a cache directory since I don't want this embedder to download the model on each run of the application. So after we have the embeddings, I'm going to be calculating their similarity score or distance metric, and we're going to be getting the indices of the similarities. So for each one, if the similarity between the chunk and the query is more than 0.1, and of course you can change this constant to something else, we are going to be creating this document chunk, document chunk actually, that contains the document path, the text, and the relevancy score calculated by this similarity calculation right here. And essentially, this is going to return a list of document chunks as a result. So you can use this to provide the AI agent with some information and retrieval using our simple rack. Now that we have the server ready to run, you can do so using Python server.py from the directory of your project. This will start a fast API application on a port of 8000 on your localhost. And in order to have a look at the MCP server itself, I'm going to be running mcp dev server.py. This will start another server, which is going to be essentially a debug and developer server on port 6274. And if you open this URL, this will open the MCP inspector. Here you can click connect. Make sure that this is the URL pointing to your localhost with MCP at the end, and the transport type is streamable HTTP. Now, if you go to the tools and click list tools, you can see here the complete list of tools that we have thus far. And you note that each of the tool has the associate comments with that. If I go to the list files tool, you can see that you have now the option to run the tool. And this is the actual response that your AI agent is going to receive when it tries to work with any of those tools. In this case, this is going to list the files that we have within our directory, and along with their path, modified time, create time, and other properties for these files. Now that we have the MCP server up and running, we are going to continue with the agent that is going to work with the tools from the MCP server, and we're going to build that on top of a LangGraph agent. So here is the system prompt for our agent. Here, the important parts are that I want the agent to know that it is a personal knowledge manager that helps users organize, search, and synthesize information from their vocal document collection. You operate entirely locally to ensure complete privacy. So this is baked in, at least as far as we can, within the system prompt. And this is the purpose of the agent: find specific information, understand connections, summarize and synthesize knowledge, answer questions with proper source attribution. This is really important. Of course, we can't expect a 18 billion parameter model in a TST format to be great at all of these, but from what I've seen thus far, Quentry is pretty good for its size. So here I'm also specifying the tools that we have. This I have found to be relatively important, even though the MCP integration will once again give the tool implementation. I'm just giving here the list of the tools and how things are working. I want that to always search for relevant information before responding, so I would encourage the agent to look through the rack information or the retrieved information instead of just thinking about its or using its own knowledge. It is again really important for us to cite the sources themselves and to say that incomplete information is the reason why it can't answer some of our questions. And here I am nudging it into a response format that I would like. I would like the model to give me a direct answer, then provide a list of sources, connections, related topics or documents when applicable, and possible next steps, suggested follow-up questions or areas to explore. And here I say the document path MD contains a direct answer here with sources and then related information. Remember, using list files will show you all the files in the knowledge base. So this is essentially the first tool that I expect the model to call during a conversation, since this will give the information or overview of the files that we have. Okay, so how is this agent built? Honestly, it is quite easy using at least the LangGraph library and some configurations. So I'm going to be creating our model. This again is going to be Quentry, the 8 billion parameter model, and I'm going to be using a memory saver, which for us is going to mean that in memory, the chat messages for the agent are going to be persisted during our chat conversations. Then I have this config, which is going to say that we're going to be using a thread or a conversation ID of 42. Of course, this is the number that we chose. And then I'm going to be using the thinking end and start tags, so I know whether or not the agent is within those modes. Then the next thing here is the chunk type. Since we're going to be streaming our responses, I'm going to be dividing the types of chunks: content, starting, thinking, end of thinking, and then a to call, since we're going to be displaying pretty much all of those states and chunks within the UI. And then the chunk itself is going to be essentially a chunk type, and then the content, or this content, is going to be a string. To create the agent itself, we're going to be using the multi-server MCP client. I found that this is actually the easiest way to work with an MCP server from the client side. You essentially initialize this class, and this pretty much hides every complexity with initializing your session and getting an instance of the MCP client. So in this case, I'm going to be using this multi-server MCP client, even though we're using a single one. Of course, you can add other MCP server here and try it out with that. Then working with that client is really easy. You just call get tools. Since this is a synchronous operation, I'm going to be awaiting for the response here. And then I'm going to be creating a React agent. This is coming from the preview section from LangGraph. What this LangGraph implementation gives you is a node for calling a model. and then a tools node, which will allow you the model to make tool calls and run the executions of these tools. So we don't have to write this on our own. It is relatively straightforward, and I have done it multiple times in some of my previous videos. Then we are going to be passing in the checkpointer, which again is going to be the memory saver, which is going to store the conversations within the memory. And the system prompt is going to be the prompt for our agent. And this will actually give us a compiled graph if you look through this. And since graph is a parent of the compiled graph, I'm going to be returning this as an instance type. Then we have another method, which is going to be the way that somebody is going to work with our agent. And this also needs to be done in asynchronous fashion, since otherwise we are not going to be able to call the MCP tools. So here we have some more, let's say, trickier way to stream the responses of our agents. But once you understand what is happening and why is happening, is again relatively straightforward. So when somebody asks us or gives us a message, we're going to be calling the agent.aStream or async stream, and this is going to return a chunk and metadata in a whoop. So here I'm going to be first passing the human message from the provided one, a configuration which was the thread ID, and the stream mode is going to be messages, since we want to receive AI messages or AI message chunks from the agent. And if the LangGraph node, which is going to be in the internal implementation of our agent, is not the agent itself, I'm going to be continuing, since I don't want to give any UI information based on other nodes, but just the agent one. And if we have an instance of AI message, and this AI message actually contains two calls, I want to give to the UI that this is actually a tool call. The tool name is tool call name, and the arguments with which the tool is going to be called is going to be tool call args. And this essentially is going to be this dictionary that I'm going to be providing to the UI. Next, I'm going to take the chunk text, and if this is actually a token of thinking start, I'm going to be saying to the UI, yep, this is a start thing, and I'm going to be flipping the boolean value here to inting block equal to true, since I'm going to be keeping a track of that. If this is a text thing end, I'm going to be do essentially the same thing in reverse. And when we are not in those cases, I'm going to be either send a thinking chunk or just a content chunk, which is going to both ways contain the text that we got from the chunk itself. The Streamlit application is where we're going to package everything together into a nice UI interface and make pretty much everything work and communicate with each of the components. So when I open this, you see that we are starting with a page configuration where we are setting the initial setup. One important thing that I want to think about when you're building such application is that we're going to be splitting the UI into two different sections. The one is going to be the sidebar on the left, and the other one is going to be the chat interface that is going to be the main or right content of the application. So here you see that I have type icons for Markdown, Python, and text. These are going to be actually material icons, since Streamlit also supports those types of icons. Next, you see that I'm initializing a cached agent using a session state whoop, and this will create our agent. Since this is an asynchronous operation, we are going to be needing to synchronize this with our session state loop. And then you see here that I have a document converter, which again is a custom function that we have. This actually is going to be a Docling pipeline. This is very similar to what I've shown you within the CAC implementation and the Docling pipeline video that I also have. So the more important parts here is that we are actually going to be using PDF and HTML. Actually, we're going to be using just PDF in our case. And when an input is a PDF, we're going to be using a standard PDF pipeline with PyPDFium, which is going to be the dependencies that I shown you at the beginning of this video. Here we have just a single helper function that takes bytes of uploaded document data and an instance of this document converter, and essentially get all of this in order to convert the document into a Markdown string, which we're going to be using instead of the PDF that the users are going to be providing for us. So after this document converter is also created, I can start by initializing the application. Here you see that we have a list of messages, the loop, which is a sync.io new event loop, and I'm going to be setting this event loop to the async.io instance. Then we're going to be creating our agent, the files, which again is a helper function, read directory files. Here we have our pedantic structure for the file information, the path, the modified time, created time, etc. All of this is actually used by the list files too as well. So this is a relatively straightforward implementation. Given a directory, we're going to scan the directory for the supported files, which are Markdown, text, Python files, and PDF files. And based on that, I'm going to be populating each and every one of those. At the end, we're going to be sorting the results and returning the results into this file information result. So, and the next and final initialization step is the call to the create converter. This will pretty much slow down your application at start, but everything after that is going to be loaded into memory and essentially ready to go. So I'm going to skip to the main function to show you the high level overview of how this implementation or application is laid out. So here we have the header with the name of the application, the subheader, the initializing of the app that I just shown you. Then we'll essentially render the knowledge base, which is going to be the sidebar, then the chat history. Then I'm going to show the input for chats. And if the user have clicked the refresh files, or if it actually uploaded a new file, we're going to be calling the read directory files function with the data directory and rerun the Streamlit application. And then on the left side again of the sidebar, we're going to be having these settings that I'm going to show you when we rerun the application. The rendering of the knowledge base is within our helper function. Here you see that we're starting with the header, and then we're going to be building a file tree which will contain the directories and the files. After we build this tree, we're going to be using this render function. Let me show you what this contains. So this essentially checks whether or not the current level or file is actually a folder. And if it is a folder, it's going to be using the material folder icon, and then recursively call this function with the contents. And if this is a file, we're going to get the file icon based on the type, that is a Markdown, a text file, or a Python file. And it is going to be showing us the Markdown and the indentation level, which is going to be this level right here, calculated thanks to our recursive implementation. And then finally, the name of the file itself. So this is a pretty straightforward recursive implementation of rendering of the tree. Then we have a small summary of the files. This will contain essentially a grouping of the different files and their sizes along with the type of files. So for example, it's going to tell us, yeah, you have 3 Markdown files and 2 Python files, and their size in total is let's say some kilobytes, and we're going to be displaying this in a second. Next is the upload section. Now here is where it becomes a bit more interesting. We have the file uploader, and we're passing the types of supported files. If not a file is provided, we're going to be just returning from this function. Otherwise, we're going to be using the sidebar with a provided path that the user can say, okay, this file is going to go through this directory and it's going to be named, etc. So you will be able to do that when you're uploading a file. And then when you hit upload, you see that it is taken care with handle file upload. Here, if no upload file is provided, we're going to be just returning. Otherwise, we're going to get the file path, remove any prefixes of the slash if theirs exist, and we're going to be getting the parent of the file and making sure that the directory for that is already created. Otherwise, we're going to continue with the suffix, and if this is a PDF, we're going to be displaying this toast saying, yeah, we're going to convert your PDF into a Markdown file, so the user knows that it might take some time. Then we have the Markdown content using our convert to Markdown helper function, and we're going to store the file with a replaced extension or suffix to .md instead of the original .pdf file. And here we are otherwise just going to be getting the file and uploading it to the file path that the user has chosen. So this is pretty much the render upload section. The next thing is the refresh files, which is going to be a simple button that just reads the directory. And once this render of knowledge base is complete, we're going to continue with the chat history. This again is going to be relatively straightforward. We're going to be storing the session messages within our session state, and based on the current role being that an assistant, which is going to be the smart toy icon or a person icon. This is going to be the avatar, and then essentially fill the message content within a Markdown block. So this is the chat history rendering. Then we have the chat input, and this is going to be the prompt that, or the message that the user is going to be providing to us. I'm going to go into this in a second. I just want to show you the higher level details here. If I refresh or upload, we reread the files, and then the rendering settings. Here again we have a reward, which is going to cache a resource, clear the whole application and rerun it. So this is essentially a hard reset for the application. This is going to be showing us the model, the provider, and the data directory that we have. The last part is the handling of a new message. So here we're going to be working with appending the message from the user to the messages. We are going to be adding this to the history before we start with the response from the assistant. And then once the assistant block is completed right here, we're going to be creating a thinking placeholder and the message placeholder. And then here we have this send message stream function, which essentially is going to fill the content from the chunks of our AI agent. Here we have the full response content and then the thinking content. So this again is done due to the fact that we need to have this asynchronous implementation. So here I'm using our async.io loop with run until complete and call this function, which is an inline here. Of course, this is a bit hacky. If you know a better way of doing this, please let me know down in the comments below. And I'm essentially importing both of those variables right here. So once we have this information right here, we are going to be using the stream agent response with the chunk data, and we're going to be passing this to the process stream chunk function, and then we're going to be getting the thinking content and the full response content. And here we'll also be using the message placeholder to give the full response text and the render thinking block. This is the final part. When the thinking is complete, we're going to be closing this expanded block. Let's go through the stream chunk. So this is the meat of the implementation. Here we are essentially checking the chunk type that we have, being that a content, a start of thinking, end of thinking, or to calling. And here you see that we have some implementations that allow us to do some of the icons and the formatting that we have. I also have a helper function that works with the material icon and tool call. Here I'm using a tool JSON block for the tool call content that is provided by the agent itself. So pretty much all of the information here is used in order to render some part of the message as it is coming or streaming. And here we have this thinking block with the think placeholder, with the thoughts, and then filling in the markdown as the tokens are provided to us. To run the Streamlit application, you need to have the MCP server already running, and after that you need to use Streamlit run app.py. Here I'm using a no watcher or disabled watcher since I don't want this to mess up with my Streamlit initialization thanks to using a PyTorch in our case. Run this. This should open your browser with the Streamlit application running. On the left, you should have your sidebar. Here, you should be able to expand the model settings, the provider, the data directory. Also, you'll be able to run the refresh files. Let's, for example, check the browsing of the files. Here, I have the NVIDIA earnings PDF. If I select this file, and for example, let's see reports, NVIDIA earnings 26, and press upload. After the upload is complete, you can see here within your knowledge base that the NVIDIA earnings 26 MD is actually now available. So the Docling pipeline run correctly. Let me close this. Okay, so let's test out the agent. Let's first start with what files do I have. And you'll note that it starts with the first thinking section. And it roughly says that it needs to call the list files function. You can see the call. And it gave us a nice overview of the files with their sizes, the type of the file. We have a Python script here. So here you can see that the thoughts are nicely removed or closed from the thinking of the model. So let's see how would this model use another tool. Let's, can you summarize the about me file? And here it makes a nice reference to about the about me MD file with the correct directory. Here you can see also that it is calling the summarize file tool with the file path argument for personal about me.md. And this is actually the file contents. My name or Slim Shady, 30 years old, location Detroit, Michigan, married with 2 children, software engineer at Meta, work focus AI models development, where I work on poor AI models. So of course, this is why you work at Meta, I guess. So the final test that I want to run for this model is to have a look at the information within the coding file. Of course, you can run some searches or see how the rack implementation works. So what is the 206 Python file about? Give me a summary of the code. Look at the whole file. Okay, so this is the report. It actually did go again the summarize file, and we have the path to the source. Actually, the file really contains list node, reversed linked list function, print linked list along with example usage. And it has actually code highlights. The reversal algorithm uses 3 pointers, previous, current, and next, to traverse and reverse the list. The example creates a single node list and shows how the reversal works. It is also citing the source, and it is asking for further suggestions about how you should continue with your conversation. I mean, like, this is next level, very crazy stuff that you can do on your local machine with completely free and local AI tools. So this is it for this video. We've seen how you can build a completely local AI agent that can work with your files using a custom MCP server. We've built pretty much everything with support of some of the great open and free libraries, and the result is pretty much astounding, at least to me. I've tried this chat AI agent, and the results are really great. The tool calling of Quentry is like next level, at least for these simple tools that I'm throwing it at. And pretty much every time that I've seen the model do a call, the parameters were on point. The list and paths that the model receives for the tool calling are pretty much every time correct. The history and memory of the model within the messages are also very nice. The thinking process can be a bit lengthy, let's say, but at the end, the results are pretty good. Thank you for watching, guys. Please like, share, and subscribe. Also, join the Discord channel that I'm going to link down into the description of this video if you want to get access to the complete source code along with the UI and the complete GitHub repository. Please go and subscribe to ML Expert Pro. Let me know if you have any questions about the implementation, the application, or in general for open AI models. And I'll see you in the next one. Bye.